All right, so yeah, today I'm going to talk about LLMs a lot. I also want to get a show of hands, like stack-wise, because I'm a Python engineer, and I know that historically NDC has been a lot of .NET. Can I get a show of hands of Python engineers in the room? Cool, two. Any .NET? Okay, yeah, all right, that's a good hunch. We're not going to go into too much code. I think I've got like one slide with some Python on it. But I'll explain. And Python is like English with brackets. It's pretty straightforward to read. So yeah, we're going to cover off today are LLMs good software engineers, which is a bit of a clickbaity title. And I'm going to go into some details as to why. But before we get started, if you want to see my website, I've got things that I've published in the past. It's tonybaloney.github.io. My GitHub handle is tonybaloney. Things that I've done over the last few years, I wrote a book on the Python compiler. Actually, my claim to fame now is I wrote a book before LLMs existed, which I'm really proud of. So I wrote it by hand, actually typed it out myself, which is pretty cool. I've worked on some optimizations to Python itself. Some of the reasons why some of the newer versions of it are faster is from work that I've done. I've written a thing called C-Snakes, where you can embed Python into .NET. If that's something you really want to do, I'd recommend you check out C-Snakes. It's a really cool project. And then I've also done this thing called VS Code Pets. Has anybody used this? OK, quite a few people. OK. Yeah, so I've done all these other things with compilers. No one really cares about that. I made cats and dogs walk around inside VS Code, and it's got 2.5 million active users. So that's what I will be remembered for forever, which is brutal. Anyway, so let's get into it. Are LLMs good software engineers? No, they're not. So thank you very much. I should have submitted this as a lightning talk. Yeah, that was the short version. I think we'll go into the long version over the next maybe 50 minutes, and then I'm hoping you've all got lots of questions because there's some pretty opinionated things in this talk, and hopefully some ideas that I can leave you with. Show of hands, who's using AI in their job today? Everybody, pretty much. Brilliant. OK, that's great. So why am I saying no? That's this. I mean, basically, if you recognize this, this is a bell curve. LLMs are probability machines. They will pick the most likely answer. That is what they're designed to do. They generate tokens based on probability. Probabilistically, they'll recommend the average code with average quality. They've been trained on huge amounts of code. When I talk about Python in particular, they're trained on beginner Python code. They're trained on the best Python code in the planet. But the bulk of the code they've been trained on is what I would say is like an average quality. When you look at .NET, there's a lot less .NET in the public domain, which is why they are not as good at .NET. And in C# specifically, the quality of the code that's generated or its ability to solve tasks is less because it doesn't have as much of a probability model. It will recommend the framework that most people use. It will recommend the language that most people use. If you ask it to build something for you, it will recommend which language? Python. It won't think about the task. It will go with the most likely answer. Now, this has been the case for LLMs, but increasingly, we've introduced all these tricks to get the LLMs to do what we want. But before we get into the details, we're going to go back in time to this really key paper. You see it had only a couple of authors, but if you've got amazing eyesight, you'll see two of the authors, Dario Amodei, who's quite famous now, and Ilya Sutskever. This is the original paper for the codex model. It's fascinating if you want to read this paper. Basically, what they're saying is we have been working on LLMs. This is like GPT-3, I think it was. And we've trained another one with code. So this is when they introduced the first codex model. And they're talking about basically, if we describe a function and we give it some document, like some just code comments, can it populate the function? And then if it does that, how accurate is the code? Now, this is really interesting, this paper, because they come up with 3 points in this paper. There's a list of warnings at the end of the paper. Number 1, it suggests code that appears correct, but does not actually perform the task the user intended. Number 2, Codex, which is the name of the model, will generate code that is as similar as possible to its training distribution. So it will basically go with the most common answer. And thirdly, because it can produce vulnerable or misaligned code, qualified operators should review its generations before executing or trusting them. So this is the paper from, I can't remember what year this was. It was about, I think it's 4 years ago, 3 years ago. But I'm happy to say we've solved all of those problems, and they're definitely not an issue anymore, so we can move ahead. I use AI a lot in my day-to-day work. I work at Microsoft. I found out recently, I got asked, what are you doing, what are you working on at the moment? Because you're in the top users in the whole company of Copilot, GitHub Copilot, in the top 10 inside Microsoft, which means that I must be costing them a lot of money. I know how much the top 2 users are costing, and thankfully I'm not in the top 5. Otherwise, it's a different conversation. But I've been using it a lot. And I'm going to talk about some traits that I've seen. And these are funny little quirks and behaviors that I've noticed in the models over the last year. Number 1, it rushes into implementations without planning longer-term architecture. When you're discussing building out a feature or fixing a bug, it will jump straight into it unless you tell it to build a plan. Unless you say, OK, let's work out and explore a problem. If you say, go and fix this bug, it'll jump straight into trying to fix the bug. Another thing I've noticed it does a lot, it needlessly reinvents the wheel. If it can't figure out how to install a package, and you've put it in autopilot mode, it will rebuild that package. I actually caught mine recently trying to rewrite GitHub Copilot from scratch. I left it in autopilot mode, and I said, I need this working. I've got a demo in 2 days. I left it in autopilot, went downstairs to get a coffee, came upstairs, and nearly spilled it all over my desk because it was halfway through trying to plan out an implementation of GitHub Copilot, the whole thing, from scratch. So actually, one trait I didn't include, because I've actually reversed my opinion on this in the last week, is that its ego is off the charts. However, if anyone's used Opus 4.7, which came out this week, they've actually quashed that down quite a bit. So I removed it from my deck. Another thing, it reaches for the same set of tools without researching the latest options. It goes on what it's been trained on, rather than thinking about what's the best framework to use. You'll see this if you write a front end, for example. It will start off with React. It won't think about the requirements unless you tell it to. It will jump into what is the most common solution. Another really challenging thing with it is that it will ignore rules and design guidelines whenever it's convenient. So if you say, whatever you do, don't do this, you put it in the instructions. If it comes across a hurdle, and again, you leave it in autopilot mode, it will work around the rules and just skip them. Even in the thinking block, you can see that it's discussed that, and it said, I'm just going to work around this for now, but it's not an issue. It gets even worse when sometimes it does that with security stuff. I've caught it once basically just disabling the security rules that I left in place because it said, oh, I'll come back later and fix those, but it never did. So this is a pretty damning list of traits. So it rushes into implementations, it reinvents the wheel, it reaches for the same set of tools, ignores rules and design guidelines, and it bypasses security when it's too hard. Does any of this sound familiar? This is like, and I'll speak for myself. I made this list, and I looked at the list, and I was like, I do all of these things. I'm criticizing the LLM, but like, as someone who's been engineering for 20 years, and has managed engineers and coached engineers and taught engineers, these are classic engineering traits. And that's because that's how we taught the model. We taught the model on what we've done as humans. So it's picked up a lot of our behaviors, and we need to start to work around those things. Now, the difference is, and this is something which is really challenging, is when I've worked with junior engineers, I've tried to coach them and teach them to get better. I've noticed over the last year, I keep trying to teach the LLM. And it's frozen. It's frozen in time. It doesn't learn. It has memories now, but that doesn't do what I want. You can't teach this thing. You can't coach it. So we actually have to change the way that we work with this as a tool and stop trying to treat it like a junior engineer that we can coach to become a better software engineer. So far, I've just talked about my opinions, but we're going to go into some data now. First of all, we've seen a huge increase in the number of AI-generated pull requests, which is brilliant. However, some studies have shown that of the AI-generated pull requests that we see on GitHub, 72% of those are not merged. People now have this great way of generating pull requests to projects, or the AI assistant can go and do it for them, and they submit a PR, and then they move on to the next thing. And one of the challenges that we've got is that we still want to maintain, as humans, we want to have a gate so we're maintaining projects, especially really critical projects. But if you're maintaining a software project now, you'll see there's like this huge swathe of pull requests that you get to open source projects. And the data we're seeing is that 28% of the AI-generated ones are merged instantly because they're small changes, and a bulk of them are too large or too complicated for the maintainers to keep up with. This has caused quite a big challenge. One of the challenges is that people who are using AI assistants a lot, all day, every day, are actually finding themselves really quite exhausted because the AI can produce code at a far faster pace than we could before. But the thing that we're using, the way that we're interacting with it is a lot of those key decisions on architecture, on the right way to do things, on security implementations. Whereas maybe 10 years ago when I was writing code by hand, the old style way, you could relax typing code and you could think about things slowly and you could spread it out over a day. And now you're trying to compact all those decisions one after another and delegating work to AI and agents. People are talking about this as this idea of AI fatigue. Has anyone experienced this in the room? OK, yeah, there's a few of you. It's not just you. I don't know if there's any studies on this yet, but it definitely is happening. I think people are basically finding that as they're using LLMs more and more, you're doing the hard decision making, and then you're using the LLM to produce the code for you. It just means you don't have any breaks in the day, and you're using a different part of your brain. I'm bringing this up because what we're seeing, I mentioned we've seen a 10x growth in pull requests from coding agents quite recently. GitHub itself has seen a huge surge in traffic over the last 6 months. Almost entirely driven by LLMs. So this is important because 80% of AI-authored PRs from non-owners, so let me phrase this another way, 80% of pull requests to projects which are made by AI from someone other than the maintainer of the project emerge without any human review. This is a study I was looking at. It's a terrifying statistic. If we go back to that paper I mentioned at the beginning, there was this warning they left us in the paper. Because Codex can produce vulnerable and misaligned code, people should review its generations before executing or trusting them. And I feel like we, as a software engineering community globally, are kind of sleepwalking into this environment where we're just trusting code that's coming in. I'm going to give you some examples a bit later where it is quite hard to spot the issues, but they do exist. And one of the issues that we have is that we've designed quality gates and checks and tools for humans, and now we've got LLMs that can produce a lot more code with different quality. We need to update our processes. That's really the key to my talk, and I'm going to go into exactly how we can do that. Now, we can use AI to do code reviews for us. Another benchmark I found called SWE PR Bench found that for things which are human-flagged code review issues, if they gave those same things to frontier AI models and asked it to check the code, it only found between 15 and 31% of them. So we still need humans to review code, especially if that code is produced by an AI, or if it's produced by a human. It doesn't really make a difference. To illustrate my point, we're going to play a game, and it's called Spot the Issues. I hope the resolution of this is good enough that we can spot the issues. And I want you to just raise your hand and point them out. I picked this image because I love it. I saw it on LinkedIn, and it was somebody just, pretty much everything on LinkedIn is just AI generated now. But they posted this talking about prime ministers, and I looked at this picture, and I would have just skimmed past it as just being AI slop. But I looked at it a bit more closely, and the longer that you look at this picture, the more issues you find with it. Put your hand up and call them out as you find them. Yeah. The wrong Anthony Albanese in the middle row. Yeah. Anyone else? Yeah. Yeah, one of the prime ministers is called, that is Bob Hawke. So third along is Bob Hawke, but he's called Meat Pies, and that is a pile of pumpkin. Anybody else? Yeah, at the back. Yeah, Paul Keating's name is Bob Hawke. Yep, that is a very good observation. Yeah, anyone else? Yeah. It says top 8. There's 12 of them. It says top 8 prime ministers. Anybody else? Yeah. There's Ronald Reagan. And possibly Gorbachev. I'm not sure about the bottom one. Oh, yeah, in the second row, there is somebody here. I'm not sure who that is. Yeah, this, oh, you can't see my mouse, can you? Yeah, second row, third along is called Australian prawns. Ronald Reagan, who's labeled as Anthony Albanese and Healthy Salads, has a burger and chips. Yeah. Yeah, Australia is actually spelt wrong as well in the Australian emblem at the top right-hand corner. That's extremely hard to see. Anyway, my point is, if you just glanced at this picture and you said, oh, here's a picture of the top 8 Australian prime ministers and their favorite foods, and you looked at it for 2 seconds, you'd be like, yeah, that is. It's an infographic. The longer you look at this picture, the more issues you find with it. And the way that this picture was created is slightly different to LLMs. They use a different technique. This is clearly AI generated, but it actually has some of the same behaviors that we find with code, which is that you really actually have to study it in quite a little bit of detail to see where it's made these tiny mistakes. So when you're looking at code reviews, I really want you to remember this picture and consider this as being something that you've reviewed on the way out. We have definitely spotted marketing agencies, big companies put out brand campaigns with things like this, where someone's looked at it and said, yep, that looks good, and then they've shipped it, only for it to go viral because there are not 8 prime ministers there. We never had a prime minister called Meat Pies, although that would have been amazing. And Ronald Reagan was never the Prime Minister of Australia. So I'm going to call on some recent data. Has anyone heard about Claude Mythos yet? Yeah. It's been in the news a bunch. It's this mythical AI model that's coming out soon. Some people maybe even have access to it in this room. It's one of the headlines for this model is that it achieves 93.9% on SWE bench verified versus 80% for Opus 4.6 and 77% on SWE bench Pro versus 54%. Okay, so why is this important? So one of the benchmarks that we use for AIs is this thing called SWE bench. Basically, it is a collection of bugs to big open source projects, all Python, which includes Django, Matplotlib, NumPy. These are issues that were raised against those repositories. And then we have a bug report. And then we have like what we call a golden patch. So here's what the solution looks like. And then we've actually created tests. So we say, like, here's how you verify that the bug exists. Here's how you verify that the bug was fixed. So what this benchmark is a list of bug reports. And you give the bug report to an AI, and you say, here's the code for Django, which is a big web framework in Python. And you say, can you solve this bug? And then the way we measure whether or not it solved the bug is we run a unit test at the end. If it passes the test, you get a mark. If it fails the test, you get a 0. So that is basically what Swedenbench is. If you look at the announcements for the AI models, this will actually be one of the first benchmarks that they mention in their sort of announcement. The way I've heard this described is this is basically like the AI's way of proving how well it can just handle and fix issues in a large code base, which is a pretty eye-watering statistic. The idea that this model could potentially fix up to 94% of bug reports on a code base is phenomenal. But if you go back to those traits I was talking about and some of the quality problems, we need to think about meat pies as the prime minister. Like, are we just like thumbs up, it passed the test? And for those of you who are like full-time software engineers or have been doing this for a while, there's passing the test and then there's fixing the issue, and they're two different things. And so there's a couple of things here. One is this thing called the Swedenbench illusion. This is I love this paper. Basically, what the researchers found is that the LLMs have all memorized these code bases. Because this benchmark is saturated, they know exactly how Django is laid out. So you can even just mention the issue number, and it knows what lines of code needs to change. They verified this by basically taking the same bug report, but then obfuscating the file names, and then asking it to solve it. It dropped the resolution rate from 23% up to 50%. So if they said, oh, we can solve 80% of issues, that went from 80% down to 30%. Because actually what the LLM was doing is because it's seen all those bug reports, there's only 200 in the collection, it's memorized them all. So the way I describe this is if you gave a kid an exam paper and you just told them the question number and they could give you the answer without having read the question, that means they're cheating, okay? So that is basically what this paper is saying, is that you can just mention the issue number, you can just mention it's Django 16139, and it knows what line of code to fix. Because the LLMs, this benchmark has been discussed by so many people, there's so many papers written about it, they've already memorized the answers. So they're effectively cheating. So a lot of the solutions involve cheating. Most of the problems that they're given, they've seen before. And if you obfuscate the file names, they kind of get a bit lost. So to recap on my opening section, the quality, I feel like, is a bit uncontrolled. The benchmarks are unreliable and definitely gamed. Software maintainers are overwhelmed with huge amounts of AI-generated code. And also, the other thing is that a lot of the models, their confidence as a model is miscalibrated. So what they feel like they can achieve or solve is definitely not lined up with what reality is. If you ask an LLM, this is a really fun test, how confident are you in the answer? If it says it's 90% confident, it is not right 90% of the time. They're just not calibrated that way. So it's very hard to measure the quality of them. So why am I one of the top users in the company if I hate it that much? And the answer is I don't, actually. I'm going to give you one example, which happened in the last week, which astonished me. And this is kind of our pivoting point in this talk, which is I've talked to you about some of the cautions, And now we're going to start discussing like the potential with what can be done, and then I'm going to start talking to you about solutions for the cautions I've given you at the beginning. So why are we bothering with this? This is a graph. You don't need to read it in detail. The QR code goes to a pull request. This is a pull request I wrote by hand, not using an AI, to a project called PyTorch, which is like a library that's used for LLM inference. Basically, my patch makes AI models run faster on this laptop by up to 50%. It's a very small patch, but I wrote a document explaining it. It's about a 10-page document explaining like CPU optimizations and how this particular batch enabled one and why it wasn't being used before. And so if you have one of these laptops, it's an ARM laptop, and you're running Windows, yes, AI is run faster on Windows now because of this small code change I wrote by hand, by exploring things, asking questions, and then trying to figure out what happened. This isn't me bragging, it's me leading up to the next slide. So I was getting upset because Git on Windows, a lot of people use Git, it's quite popular. I find it quite slow on Windows, and I wanted to understand why is Git on Windows slower than Git in WSL on the same laptop. So I had this kind of question. I was discussing it with the Windows team, and we had a bunch of theories. I realized that the antivirus on my machine, constantly scanning the Git repository, was one major contributing factor. But I said to the AI, I said, I've checked out the source code for Git. I've written a benchmark to measure like the Git performance. There's some tools here to do tracing, so you can understand exactly what's happening. I have WSL. I have Windows. I want you to run this benchmark and experiment with solutions, and also read my paper from that patch I showed you on the previous slide about CPU performance, because that might be one of the issues. Left it. I went out for the day with my kids, came back, and it said I finished. I was like, great, but let's review the work. And it's like, what I've circled on the right-hand side is the performance gains that it talked about. And it said, OK, I found that the way that we do hashing in Git could be improved on ARM processors. And based on the stuff that you put in the document and the patch, and it's got the pull request ready, we can improve hashing in Git by up to 50%. And I said, great, but just on Windows, right? I work at Microsoft. It said, no, just on ARM machines in general. I was like, oh, OK. I'm not sure what to do with this, because I've left it alone for a day, and it's worked out a better way of doing hashing in Git that can improve it by up to 50% on every machine with an ARM processor, which is mind-blowing. I basically gave it all the information to get to that point, but left it alone, gave it the tools, gave it the feedback, and gave it the mechanism to run benchmarks. And when I scrolled back through the history, it had a couple of theories. It made some iterations, and it said, oh, yeah, this will make it faster. And it ran the benchmark, and it made it slower. And then it tried something else, and then it made a little bit of difference. And then it kind of went backwards and forwards. And then it said, oh, this is the thing you mentioned about how ARM processors have got this built-in instruction, which is really good for SHA-1 operations. And actually, let's try using that instead of the way that's written at the moment. And it was like, oh, that makes it a lot faster. Do you want me to submit that as a pull request? And I was like, no, please don't do that. Let me investigate it properly and understand exactly what's happening and just verify. Because I tend to get overexcited with optimizations. I'm like, actually, it made one initially. It was like, oh, I've made Git 10 times faster. And I was like, how did you do that? And it was measuring it based on like the process time. And I looked through the logs. Actually, all it had done is it had caused Git to segfault. So it was like, it ran 10 times faster because it launched the process, and then it just like segmentation faulted. And it's like, hey, it's 10 times faster. I'm like, no, that's not a solution. I'm not submitting that as a pull request. Anyway, this fun story side adventure is that could a human have written this? Yes. I probably could have worked on this over a month, maybe, of exploration, of changes, of research. There's a colleague I know at ARM who's done some similar things to this. Like, if we'd have sent them this, we could have discussed it, had several meetings, and probably could have put a patch together that would have looked similar to this. But it did it while I was out at the beach with my kids. And I think that is the difference, is that we now have this tool that can work on things without humans being the bottleneck. And sure, the code that it puts together is not fantastic, but if you give it the mechanisms and the controls, it can produce really interesting solutions. So where I found that people are using, actually I'm going to skip this and just go straight to solutions. So basically, how do we get from meat pies as prime minister to you're leaving it alone and it coming back and working out a way to make Git hashing twice as fast? And that is the second thing I want you to leave you with today, which is this spray bottle. If you does anyone here have a cat or a dog? Okay. This is a training technique. I don't know if it's mean. You can spray animals like with a bit of water as like a way of telling them off. This is the second thing I want you to remember from this talk today, which is you basically need to introduce lots of ways to say, no, bad LLM, don't do that again. But you need to keep doing it. The difference is that when you're training an animal, they eventually learn over time. So I have a dog. He's very well behaved, like 90% of the time. It's very exciting. He'll sit when he should be sitting. He won't chase after things. But every now and again, he will do that. If I take him to the beach and he gets overexcited, he'll sprint off. But he has learned over time, but it's not perfect. LLMs, stop trying to coach the LLMs and just try and introduce more ways to measure what it's doing and get it to correct itself. And so these are basically things that we've done for a long time. Is linting, testing, code reviews, lint the tests, test the tests, review the reviews. You basically try and introduce as many mechanisms as possible. One word of describing this is back pressure, which is like a fancy way of just saying same spray bottle, which is like introducing ways of getting the LLM to correct itself. If you just accept the first code that it produces, the chances are it has bugs in it, the quality is not great, it potentially has security issues. All of these gates and tools that we've had with like CI/CD are really important, but they're now way more important than they ever were. The difference is that it can get the feedback, make a fix, and submit a second version way faster than you would have done if it was just humans. But even with these tools, there's definitely still a gap. And I've blocked this out because it doesn't matter who it was. I don't know who the person was. And this is another story. So this was an open source project. I raised a bug report against the project, and it was saying this causes it to crash. There's a dependency that doesn't need to be there. Somebody raised a pull request against it, tagged me, and asked me for a review. It was a 300-line fix, and I had a hunch, didn't know for sure, but like the fix to the code should be 2 lines. And they submitted a 300-line PR. I could tell just by looking at the PR, it was AI generated by someone that didn't understand the problem that was being discussed in the bug. So what they'd done is this is happening a lot now. People are basically getting scripts to poll big open source projects and basically say, look at the issue, generate me a pull request and submit the pull request without a human ever having looked at any of this. They're basically trying to automate being an open source contributor, much to the delight of actual open source maintainers who now have all these thousands of PRs coming in that they have to review. I looked at the code in the patch, and it was like 300 lines of code, and it just very bizarre code. I responded with, yeah, this was to technically fix it, like the tests were passing, but the PR could possibly be 2 or 3 lines, not 300 plus. Let's discuss on the bug report what the problem is before we jump into a fix. The person replied back with a suspicious number of emojis and use of bullet points and markdown headings about why 300 lines is the right solution. So not only have they not bothered to think about the bug that we're discussing, they hadn't even bothered to read what I'd said and think about it. They told their Claude code or whatever it is to like write a response back to me about why I should accept their pull request, which made me really upset in a nice way. I didn't get angry at all. So I reviewed their PR. I left about 150 comments on it and went through it line by line, and then the PR got abandoned. So it goes into that 70% number that I showed you earlier in the talk. But that left me with a question, which is, how many PRs has this happened to where it probably could have been 2 or 3 lines, but the person who didn't understand the issue that was being discussed got the LLM to write a fix, and then it just got merged because the tests were passing? And do you remember we talked about that SWE benchmark earlier, where basically it just says the test passed, brilliant, and then like it gets accepted? So I thought it'd be interesting as an experiment to actually look at the solutions in SWE bench and compare the human fix and the AI fix. And I picked out this one example for the same bug. On the left-hand side is the human fix. This is the Django one I mentioned. Basically, they're changing the string in a parameter. That's the fix. You add ... / self-instance PK in as a format string. The right-hand side is one of the LLM-generated fixes. I apologize, as most of you are not Python developers. Basically, what the right-hand side does is the same thing with more steps. The code passes, the tests pass. They've introduced a function, which is only ever used once. The function just formats the string and sends it back. It has a guard clause in it for no reason that could never be reached. Like, the complexity of the solution on the right-hand side is far greater than the one on the left. So we basically have something which looks fine, like passes the tests, and we've got Ronald Reagan labeled as Anthony Albanese with a burger labeled as a salad. Like, it's not the same thing. So how can you measure the differences? There's several things that have existed since the 1970s for measuring code quality: cyclomatic complexity, cognitive complexity, which is a slightly newer one, maintainability index, and then like the number of lines of code. So I thought, would it be interesting to basically just like mass measure the complexity of code that's being generated by LLMs? I actually have a tool for that I wrote years and years ago, before LLMs, by hand, called Wily. And so the problem with Wily, though, is it was written for human code, and we write really slowly, so it was slow. It was a slow tool. It took a while, and I needed something a lot faster. So I rewrote it in Rust. And that's the answer to everything these days when you want to make it faster. You just rewrite it in Rust. And what it can do is, here's a graph, the performance of Wily versus everything else. It can scan 500,000 lines of code a second and calculate all those metrics on the previous slide, basically faster than you can check the revisions out on disk. It's ridiculously fast. I had it running on a 64-core server, and it was using all cores at 100% usage, basically going through Django information. Now, the reason I put this together is so that I could basically scan huge amounts of code to understand how much of the code that was generated was more complicated than it needed to be. So the study was to basically take the SWE bench results, look at the issue, look at the golden patch, look at the LLM-generated answer, and then compare the complexity against the two things. that's like one experiment to see like how much more complicated it is. And then the other experiment is that when the LLM produces its patch, can I actually just give it the delta for the complexity and say that, oh, you've written a patch, the delta in complexity, so the change in complexity, and like cognitive complexity and cyclomatic is different. Cyclomatic is like the number of branches. Cognitive is like how hard it is to understand. It's like, they're quite similar, but slightly different. If I just tell the LLM, like remember the spray bottle again, if I just say like, you've added some branches, can you do that in a simpler way? Like, what's the difference? So what I found is the complexity growth reduced by up to 27%. The lines of code reduced by up to 23%, but the pass result for the tests was less than 1.4%. So basically, if you just tell the LLM when it produces its first patch, like this is how much code you've added, this is how complicated it is, can you do that simpler? It will do it simpler. Actually, there's another result I was trying, Gemini as well, Gemini Pro. That one's also very receptive. I could get up to 40% less patches, and the pass rate is the same. So that raised a question. Let me simplify that again. So when it produces the code to solve a problem, and the tests pass, and you would normally just merge the results, you say, is there a simpler way of doing that? And it can produce the same solution, well, not the same solution, it can produce a solution with about a quarter, like 3/4 of the code that only has like a negligible difference in the test pass rate. And if the test does fail, you can just tell it the test failed and it'll fix it anyway. So the question is, how much of the code that we got AIs to write over the last year and a half is actually redundant? Like, if you put it that way, how much of the PRs that we merged included if statements that didn't need to be there, included functions which are only ever called once, include all these little quirks and behaviors where it's introduced code and all the tests pass, and the code review is fine, and then we've merged it anyway. Now, the other thing I wanted to see is if you up the reasoning effort in the model, so like if you run it an extra high, does it try even harder to make a better solution? And I found that actually the higher the reasoning effort, the more redundant code it would produce. Low is like wild, it just, yeah, don't use it in low mode, but all of these, basically, the higher up the reasoning effort you went, the more like branches it would add. So it's not sort of creating these patches artisanally, it's adding a lot of redundant code. Now, this isn't a problem at the moment because we've only been using these tools at this volume for the last like 2 years maybe, max. But over a 10-year period, like how much code are we going to add over time that then needs to be refactored? Or how complicated the system's going to get to the point where the LLMs themselves can't understand them because they've added all these branches and statements and things. So there's a couple of things we can do about this. And there's a few experiments that we've been playing with. One is that you can basically use agents to experiment with different versions of implementations. And this is similar to what I was talking about before. But we call them deep. So deep agent is where you're running like an agent harness, like Claude Code or GitHub Copilot or OpenHands. They're called deep agents. So you basically run two in parallel, and you give it a similar task, and you give it lots of quality gates, and then you get each other to review their work. That can dramatically improve the quality of the code that's produced at the other end. But really, a lot of it comes back to that we need to have a good stack of tools to measure the quality of code. And this isn't a new thing. All of us that have been working in engineering for a long time know that we have CI/CD. But typically, we introduce these tools when the project kind of gets mature, or we have someone who's got the time to do it. Okay? You don't, well, some people do, but you don't tend to write tests first. You don't, unless it's test-driven development, and there's a whole different discussion. You introduce tests once you've kind of prototyped things. You introduce linters once you're kind of like happy with things. Now it's a bit easier. You introduce security scanning tools when you think you're actually going to deploy it into production. You introduce like test coverage, like that's a whole other subject. But the thing is that the earlier you introduce these tools when you're using AI, the quicker you get to an answer that's usable. And I think that's probably the big difference, is that when you're working with senior or experienced engineers, like they can kind of work through those things to the point where they can build a solution. But when you're using AIs a lot, you need to have all of these gates in place, all these spray bottles, that you're just saying, continually getting it to something else external to the system to verify its work and give it the feedback. And where in CI/CD, having all of these linters and checkers would make developers pretty annoyed because it slowed them down. With AI, I find that it actually accelerates the work because it gets you to the answer a lot quicker, because it can just make revisions and patches a lot faster than we could with humans. So the other technique that I recommend is having multi-agent reviews. We've introduced AI as code reviewers, but it's a lot more effective if you actually create a skill where a reviewer has a specific task and a domain. So they're looking at code correctness, they're looking at complexity, they're looking at security, they're looking at readability. So you introduce these new evaluators with different domains. GitHub Copilot CLIs, adding this now, there's a /review command. You can start to build these up as skills. I'd say, like, as engineers, we should all be understanding how to put these things in our toolbox. I promise you will find that you can produce answers far, far quicker and get to like production-grade software faster if you introduce these review tools. Whilst I said at the beginning of the talk that AIs only catch a small percentage of issues that humans would catch, you still need a human to check the code at some point. Otherwise, you get to that thing I talked about where it's like, I made Git 10 times faster. And if we hadn't got a human to read the logs, we could have just shipped that. I could have submitted a pull request to the Git project. They could have had another AI review it and then say, yep, the tests pass. And then everyone's like, why is Git segfaulting? It's faster now. So this is something I want you to think about is how can you introduce these different types of reviewers into your code process, and what aspects are they looking at? One other consideration is that all this time I've been discussing this SWE bench issue on the Django project. The Django project would never have accepted that pull request in the first place. They actually have contribution guidelines saying that you have to review and verify all AI-generated output. Unverified output makes unnecessary burden and slows down meaningful progress. And one of the maintainers said, it's basically saying, please do not send us AI-generated pull requests. So we've made this benchmark around whether AIs can contribute and fix bugs in these big open source projects. But the maintainers are actually saying, no, we have people who can do that already. Please stop sending us these spammy pull requests and help us with other things. There's other things that you can help us with. So spending tokens to generate patches for tickets is not helpful if the contributor does not understand the solution. And actually, there's lots of other ways that people can contribute to open source. So if that's something you really want to get into, I recommend that you look at the project's contribution guidelines and see if they have discussed the usage of generative AI and what their guidelines are. Because if they do have guidelines, I can guarantee the AI will ignore them. So in summary, you should evaluate early, introduce quality controls earlier on, introducing the spray bottle. You should think about and design tests early on. Getting AIs to write tests is brilliant. Go and read what it created. Have a look at how it tested it. If you tell it to make integration tests, check that it hasn't just monkey patched everything under the sun. If you ask it to make unit tests, check that it's not just asserting the implementation behavior. There's lots of things that you need to go and look at and understand. And none of these are new techniques. These are things that we've done in software for a very long time. And so add these automated gates everywhere, and I guarantee you will get to better quality software, and you can produce some really impactful things whilst you're at the beach. Thank you very much. And we've got about 8 minutes left for questions. If you want to see anything I've written in the past, it'll be up on my website. Otherwise, we've got Q&A now. Thanks very much. Questions? Otherwise, I'll go back to the Prime Minister slide, and you can keep. Honestly, you can play this game all day. Where is it? Okay. Any questions? What else? Yeah, so the question was the 300 lines of code, could that be fixed by having like an automated review? Yeah, I did actually try that. I added the automated review, and it reviewed the code. And it nitpicked various things, but it never actually just stood back and said, does this need to be 300 lines of code? Like, it was just looking at it as a line by line, is there anything wrong with this code? It didn't look at like the implementation and think about, does this solve the problem in a way that doesn't need to be solved? Yeah.
Just taking that same thing as an example,
Mm-hmm.
you have tested that with certain versions of the LLMs in the current, whatever is available, right?
Yeah.
But do you see in the future,
Yeah.
where it could spit out
Yeah. Yeah, so I'll repeat the question. So the question is, do I see in the future the LLM can actually produce better answers? Yes. They're getting better each time. The models are getting better. There's a discussion, so Claude Opus and GPT 5.4 are quite expensive models. We have cheaper models that we can use. We measure cost based on like the total cost for it to fix a problem. Some of our teams internally have found that it's actually cheaper to use the more expensive model because it's smarter and it gets to the answer faster. That's not always the case, but that does happen. And we're finding that with each iteration of these models, that they're definitely getting a lot smarter. I think if we are more selective with their training set in the future, if we're picking quality code rather than just swathes of code, and then it can probably produce better answers. Yeah, I think the next few iterations over the next year are going to be pretty crazy. But yeah, we should all be automating all of our checks as much as possible. Yeah. Any other questions? Or any other Prime Minister observations that you spotted?
Do you have any advice for the human reviewers maintaining or preventing model and knowledge system? Like if the humans still need the human review process, how do they stay in touch with things and take things less direct?
Yeah, so I'll repeat the question. The question is, for the human reviewers, how do you kind of stay in touch with the lay of the land, like what's actually in the system, especially if the rate of code change is now accelerated. So a couple of things you can do. One is like LLMs are incredible summarizers. Like it's one of their like best behaviors. So like summarizing changes to the system in the past week, summarizing changes to the layout, summarizing like architectural differences, looking at like documentation and saying, should that documentation be updated because of these pull requests? Like they're very, very good at that. So updating like a model that you can look at and it condenses information. So when you're updating your like mental model of what's in the system, you're only looking at a summary rather than trying to read every pull request, if that makes sense. So that's one thing you can do. The other thing is that you can have different AIs review the same code. That's something we're doing a bit more now. And then you as a human are thinking about what is the AI not checking for. So we still need humans to check things, but leave the nitpicking to the LLMs because they're quite good at that. But think about more sort of stepping back and does this code need to be there? Like, does that approach make sense? Like, what's the long-term impact of that change? So like thinking about those other kind of review decisions that the LLM just doesn't have context for. Yeah, I hope that answers your question. Otherwise, we can chat afterwards. Yeah. Anyone else? Cool. OK, all right. Thanks very much, everybody. Enjoy the rest of NDC.